Welcome to our discussion on logarithmic functions. As always, you can fast forward to the particular topic you want to see. Let's start by defining what a logarithmic function is. So you have to have a positive x value greater than 0. A has to also be positive and not equal to 1. And then we define y to be the log base a of x if and only if x is equal to a raised to some power. So a log function really is an exponential function in disguise. It's actually an exponential function in reverse. They're inverses of each other. This log base a of x equals y is really asking the question a to the y, right, equals x. It's saying what power do I have to raise a to in order to get x? Okay, so you can always rewrite a log function in terms of an exponential function to help you kind of figure out exactly what's being asked. Here are some simple examples. We know that 4 cubed is 64, so we can see that log base 4 of 64 equals 3 because it's asking the question 4 to what power ends up equaling 64, right? 1/2 to what power equals 1/16? And the answer is 4. A to what power equals 7? So a to the negative 2 equals 7, and then you could try and solve for a. We can also go back and forth from a logarithmic equation to an exponential equation. 3 to the 5th equals 243. 2 to the x equals 5. A to the x equals n. It's a good skill to have to be able to go back and forth between these two because sometimes it's easier to solve in one form over the other. So it's good to be able to write it both ways. How about evaluating them? Trying to find some logs is easy if you just rewrite them. Some of them require a calculator. For instance, a is an easy one, right? We know that we're just saying 5 to what power equals 25, and you go, well, 5 squared equals 25, so y equals 2. Simple. 2 to what power equals 16? Again, pretty easy to figure out. It's 2 to the 4th, so y equals 4. 1/3, right, to what power equals 9? Well, we know 3 squared is 9. 1/3 squared would be 1/9, but then to flip it, it's got to be negative 2, right? So negative 2. Obviously, 7 to the 1 equals 7. 6 to the 0 equals 1. And then 4 to what power equals 1/2, right? Well, we know that 2 to the minus 1 equals 1/2. We know that 2 to the 2y, right, is what 4y is. So by substitution, we know that negative 1 has to equal 2y. And then very easily we can do the algebra and get y equals negative 1/2. Now what about something like this that isn't so obvious? 5 to the negative 3rd equals x. We can do that, right? We can do these straight by just doing z cubed, however, equals 1,000. That's a little bit backwards, right? 5 to the negative 3 equals x. That's simple. We just do that. Just raise 5 to the negative 3 and we get this answer. Similarly, 3 to some power equaling 1/27th is not too difficult if you rewrite the left-hand side as 3 to the negative 3. And then because the bases are the same, we know the powers have to be the same, and y just equals negative 3. That's going to be a very common way of solving these. Again, z cubed equals 1,000. Well, if you can make them match, right? Now the base is z instead of the power. Right here we didn't know what the power was, so we had to make the bases match and then match the powers. Here, since we have the power, get those to match, and then the bases have to match. So z equals 10. Are you seeing the pattern? That it's always, if two things are equal, both the bases and the powers have to be the same. So if you can ever match up the base, left and right, then you always know that the powers are the same. Or if you can match up the powers, you know the bases are the same. Finally, the last piece, or the last example I should say, 2 to the 1 equals this. Very simply just means this stuff equals 2 to the 1, which is 2. Because we recognize this as a quadratic, we know we have to bring the 2 over and set equal to 0, which gives us this. Then we factor it, set each of those equal to 0, and get our two solutions of 2 and 4. How about domains of logarithmic functions? Well, the domain of any log function is always going to be 0 to infinity. And the range is always going to be negative infinity to infinity. If we try and take logarithms of 0 and negative numbers, those are not defined. Because remember, how do these things work, right? This function, log base a of x equals y, is the same thing as saying a to the y equals x. Remember, when we talk about domain, these things are going in for x. So how can we let this equal 0? Right? That's why this is a round bracket, because if x equals 0, it's now saying a, which remember has to be a positive number. A positive number raised to something has to equal 0. That's impossible. So that's why we can't have 0 into these things. It's also why we can't have negative numbers, because if a is a positive number, how can we take a positive number and raise it to any power and get a negative number? Okay, so that's why your domain is 0 and above. And then your range is everything. Finding the domain of this thing, well, again, we know we have to be 0 and above into the log function. So that means this whole piece, everything inside the parentheses, has to be greater than or equal to 0, which is where we get this. And now it's just a matter of solving for x. Move the x over here and we get x is less than 2, and there's the domain of our function. Everything from negative infinity to 2. Simple, simple, simple. Graphing them. Well, again, remember our base is greater than 0 and it's not equal to 1. So we have a couple properties. We know log base a of a just equals 1 because it's asking that question, a to the 1, right, equals a. So, right, it has to be 1. A to what power equals 1? It's got to be 0. A to what power gives you a to the x? It's got to be x. And then here, if we take a number and raise it to the power of log a to the x, let's do it over here, log base a of x equals some number y. We don't know what it is, but we know if we rewrite this, this says if we take a and raise it to this power, we get an answer of x, right? That's what it says. If we take a and we raise it to this power, we get the answer x. Well, log base a of x equals y. So if we take a and raise it to this log base a of x, we're really getting a to the y, which we just said a to the y equals x. So you can see taking the base number and raising it to a power of the log, they undo each other. These things are inverses. So a power of a log and a log of a power, right? Because here's a log of a power, gets you back to x. Inverses. Sketching graphs. Really, the easiest way to sketch graphs if you don't have technology is always give yourself a table of values. So pick a bunch of x's, plug them in, get a bunch of ordered pairs, connect the dots. Here's what a log function looks like in general. This is log base 3 of x. You can see that it snugs up here next to the y-axis. It crosses at the point 1, 0, and then continues to grow at a slowing rate, right? It's still growing, but it's growing at a slower and slower rate. It does continue to go forever, right? So its upper bound is still infinity, and its lower bound is still negative infinity. That's why we have the range of all numbers. but it's growing at an ever kind of decreasing rate. If we plot the two functions together, log base 3 of x and y equals 3 to the x, you can see that they are perfect mirror images of each other across the line y equals x, and that means they are inverses. So if we put them side by side, we can see properties of exponential and logarithmic functions also show that they're inverses. The domain of one ends up being the range of the other, right? The domain of the log function is the range of the exponential function. So that's one key element of being inverses. For exponential functions, we have that the y-intercept is 1. So that means we always have the point 0, 1. And there is no x-intercept. Here we have the x-intercept is 1, which means we always have the point 1, 0, the exact opposite, right, inverse of that one, and there's no y-intercept. For the x-axis, y equals 0 is a horizontal asymptote, right? For exponential functions, we always have the horizontal, the x-axis as a horizontal asymptote, and then for the logarithmic function, we get that the y-axis is a vertical asymptote. Again, inverses. Everything is switched. The functions are 1 to 1, and we know that if a to the u equals a to the v, that only works if u equals v. We know that if log base a of u equals log base a of v, that only works if u equals v. The function is always increasing if a is greater than 1 and decreasing in between 1. The function is always increasing if a is greater than 1 and decreasing if it's in between. Here's some typical graphs. So your standard log function when a is greater than 1 is on the left. Standard log function when it's in between 0 and 1 is on the right. You can see they both still pass through that point 1, 0. They both get asymptotically close to the y-axis, right? And they both have a range of all values. We can graph things using our information and our knowledge of transformations. If we know what log base 3 of x looks like, then the plus 2 is just going to move it up by 2. We know that the minus, right, flips it north to south. We know the minus on the inside flips it east to west. And we know that the minus 1 on the inside shifts it left and right, in this case to the right by 1. So there's our first example, shifted up by 2. Domain is still the same, range is still the same. The next one shifts to the right by 1. Domain now gets shifted to the right. So instead of the domain going from 0 to infinity, it now goes from 1 to infinity, and it now has a new vertical asymptote here at x equals 1. When we have a negative on the front of it, remember that flips it north to south, right? Flips it vertically. So it still goes through that same point, and the distances now become mirror image of each other. So we still have positive infinity to negative infinity. So we still have the same range, and we also still have the same domain because it hasn't been shifted left and right. Next we have the negative on the inside, which flips it left to right, east to west, flips it over the y-axis. We still have the vertical asymptote being the y-axis. We still have the same range. The only difference is now the domain is flipped. Instead of going from 0 to infinity, it goes from negative infinity to 0, which of course this is a typo. It should be negative infinity to 0. The log with base 10 is called the common log, and it's written without the base. Kind of like how when we take the square root of something, right? The square root of x is just that, but if we want to take the cube root, we put a 3 in there, right? When there's no number at all, we just assume it's the square root because that's the most common root that we use. Well, log base 10 ends up being the most common log base, so we just get rid of that number, and we know that whenever there's not a number, it's 10, and if it's anything else, it has the number there. The same basic properties apply, right? Log of 10 equals 1, because there's really, remember, a little invisible 10 here, and it's saying 10 to what power equals 1, and you go, or sorry, 10 to what power equals 10, and you go, well, duh, it's 10 to the 1. And then log of any base of 1 always equals 0, because whatever this number is, you got to raise it to 0 to get a 1. If the base is the same here, right, so we got base 10 equals 10 to a power, then we just get that power, and then of course 10 to the log base 10 of x gets us back to x. These are those two inverse properties, right? This is because they're inverses. We can use transformations to sketch graphs, i.e. we can put everything together that we saw from the previous graphs. Where do you start? Well, you always start with x. Plug a number into x and then ask yourself what's the first operation that happens to it. Well, the first thing we do to x is we subtract 2 from it, which means the first thing we do is we shift it to the right by 2. So instead of going through 1, 0, it now goes through 3, 0, and we now have our vertical asymptote at 2 instead of at 0. Okay, what's the next thing that happens to it? Well, technically the next thing that it does is it takes the log of things, right? And then the next thing it does is it has that minus in front of the log, so that's what flips it vertically. Then it has 2 minus that, which is the same thing as just minus the log plus 2. So the next thing is to add that 2, so it shifts up by 2. Using logarithms to evaluate exponential equations, it really comes back to the idea that these things are inverses of each other, so we can interchange them. So another example of a common log is e. All right, we've got log base 10 is called the actual common log. Another log that is used a lot is base e, and that one actually happens in nature a lot, so it gets the name the natural log. And instead of writing log base e all the time, because it happens a lot, we also gave it a special name and we just call it ln for natural log. You might say, well, why is it ln instead of nl for natural log? And it's because it comes from the French logarithmic naturel, right? Plus it kind of matches log a little bit better because they both start with L. Anyhow, here's the natural log. Is just saying that we're now doing a base of e, right? It goes back to e to what power equals x. So e to what power equals x. Same properties as before. If the bases are the same, it's a 1. If this is a 1, it's a 0. And these last two are because of the inverse idea. Now we can evaluate some expressions that involve natural logs and e's. E to what power equals e to the 4th? And you go, duh, it's 4. E to what power equals 1 over e to the 2/5? Well, that's e to the negative 2/5, right? Because this is the same thing as just e to the negative 2/5, so we get negative 2/5. And then the last one says e to what power equals 3, and we would have to use a calculator. You can actually just type in natural log of 3, and you get that number. Okay, doubling your money. How long will it take to double your money if it earns 6.5% compounded continuously? And at what rate of return, compounded continuously, would your money double in 5 years? P is the original amount invested. The amount that's going to be in your account once it's doubled is always just going to be 2P. So we can now plug that information into our normal continuous compound interest formula, right? So now A equals 2P. We're trying to solve for the time that it takes to double when our interest rate is 6.5%. We can divide both sides by P, and now we just have 2 equals e to some power. We need to solve for t, and t is trapped up here as a power of e, right? It's trapped in an exponential function. And what undoes exponential functions is logarithmic functions. And instead of taking the log of both sides, we want to take the log of the same base. And since our base is an e, we're taking log base e of both sides, i.e. the natural log of both sides. So natural log of 2 is going to equal just this stuff, because if we take natural log of e to some stuff, it goes away, right? Natural log of e to a power equals, well, this says e to what equals e to that stuff, and you go, well, it's just that stuff, right? Whatever this number is up here, you have to raise e to it to get e raised to that number. So that's why you just get 0.065 t. They undo each other. They're inverses. So now to solve for t, the last thing you have to do is just divide by 0.065, and you get roughly 10.66 years. So it'll take almost 11 years. It'll take 10 and 2/3 years for your money to double. The second part, at what rate, right? It wants to know at what rate of return, compounded continuously, would your money double in 5 years. So instead of figuring out how long it takes for your money to double at a given interest rate, they're basically asking if you want your money to double in 5 years, what interest rate do you have to get on that money? Same formula, only now we don't know the interest rate, but we do know the time, right? We plug in 5 for years. We don't know R. We still want our money to double, so instead of just being some arbitrary amount, it's exactly twice our starting amount. Divide both sides by p, and we're back to 2 equals e to the 5r. And you can see the steps from here on out are the exact same thing. In order to solve for the power of e, we got to take a natural log of both sides, which strips away that e. Then to solve for r, we divide both sides by 5, and we simply just do natural log of 2 divided by 5. We get this, and that means you basically need 13.86% as your interest rate. Newton's law of cooling is a very scary looking formula when you just look at it. A lot of stuff going on there, right? But don't worry. T is just the temperature of an object at some time. Ts is the temperature of the surrounding, so it's the environmental temperature, right? So if it's stuck in a freezer, you put the ambient air temperature of what the freezer is. If it's outside, it's the ambient air temperature. If it's submerged in a liquid, it's the temperature of that liquid, right? It's whatever is surrounding the object. And then T0 is the value of T when we first start. So anything sub-zero is always an initial. So this is the initial temperature of the object. This is the temperature of the object after a certain amount of time, right? That's the answer to this formula. We start with a certain temperature. We have some temperature of its surroundings, and then we get this exponential function in terms of time, t. And once we compute all that, it spits out an answer, and that answer is the actual temperature of the object after whatever that time t happens to be. So an example, the local McDonald's franchise has discovered that when coffee is poured from a coffee maker whose contents are at 100 degrees Fahrenheit into a non-insulated pot, after 1 minute, the coffee cools to 165 degrees Fahrenheit if the room temperature is 72 degrees Fahrenheit. Now they want to know how long should the employees wait before pouring the coffee from this non-insulated pot into cups in order to deliver it to the customers at 125 degrees Fahrenheit, right? 180 would be too hot, 165 would be too hot. How long does it have to sit around until it's at 125? Okay, we plug in everything that we know. The starting temperature of the coffee was 180. The ambient room temperature was 72, so that's why it goes in for the T sub S. We want to know, and this is not a typo, they didn't go from 180 to 108, they did 180 minus 72. That's why you have 108, right? So here's our formula simplified. Now we plug in 165, we plug in T equals 1, and this is going to help us solve for K, our constant. So because they told us after 1 hour it went to 165, right? After 1 hour it went down to 165. So we need that initial point to solve for K. We put in 165, we put in 1 for T, and you end up solving and you get K, your constant, is equal to this big ugly looking thing. Now we can plug that back in and solve for the final answer, which is, right, how long will it take to cool until it gets down to 125. So here we are back to our original equation, right, our simplified one with the 108e to the negative kt. We solve for k, so we've got this big ugly looking number up here for k. We want to know how long it's going to take until t is 125, so we put that in for t, the temperature, and we're solving for little t, the time. Subtract the 72 over, divide by 108, and now we've isolated e, right? We're still trying to isolate our variable. We need to rescue t from this power, right? Get it out of an exponential, so we take natural log of both sides. This 53 is just 125 minus 72. So natural log of the left, natural log of the right. Natural log of the right, of course, just gets rid of the e, and we now just have the power. And then to solve for t, we divide both sides by this negative number. So it's going to be natural log of this thing divided by negative 0.1, so they just wrote it as times a fraction, but you get the idea. You're just divided by negative 0.145, blah, 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 blah. And it comes out to be 4.76. Now remember, this was in minutes, because when we were solving for K, it told us that it went to 165 degrees after 1 minute. So everything was in terms of time in minutes. So the employee should wait about 5 minutes, and then it'll be cool enough to serve. We've already seen the growth and decay model before, so let's do some more work with this function. In a large lake, 1/5 of the water is replaced by clean water each year, maybe due to rainfall, or how fast a river flows in and out, or maybe just the locals do it, right? A chemical spill deposits 60,000 cubic meters of soluble toxic waste in the lake. Soluble just means that it dissolves. So 60,000 cubic meters of toxic waste are now mixing around in this lake. And there's really no way of taking it out. It's not like oil that sits on the surface. This stuff is just mixed in. They want to know how much of this toxic will be left in the lake after 4 years. And then when will the toxic chemical be reduced to only 6,000 cubic meters? Well, these questions involve exponential growth and decay. If 1/5 of the water in the lake is replaced by clean water every year, the decay rate is -1/5, right? Every 1 year, when t equals 1 year, the rate of the water is reduced by 1/5, so -1/5. And the starting rate of, in this case, the toxic chemical is the 60,000 cubic meters that were first put into it. So A sub 0 is our 60,000. R, the rate of decay, we're losing 1/5 of the lake every year, right? It's being flushed out. So 1/5 of the bad stuff, this toxic stuff, is also being flushed out each year and being replaced by clean water. So here's our simple formula that gives us the amount of toxin in the lake after a time t. Part A wanted us to just simply figure out how much was left, right, after 4 years. So you simply put in t equals 4, very simple math, plug it into a calculator, and you get about 27,000 cubic meters, a little less than half. Now the other one seems trickier, but it's still pretty easy. They just want to know what time will reduce the level down to 6,000. So a level of 6,000 just means A equals 6,000, and we're now solving for t as the unknown. Just like before, we need to isolate this thing and get it out of that power. So the first thing we do is divide both sides by 60,000, which gives us 1/10. Written as a decimal might make it a little easier. And then to get t out of this exponent, we take the natural log of both sides, which just gives us the -1/5 t. And then to solve for t, multiply both sides by -5, and we get 11.5 years. It's going to take 11.5 years to get it down to 6,000 cubic meters. So a long time, right? If that ends up being, let's say, the acceptable level where you could go swimming in it again and not get rashes and things like that, then it's going to take 11.5, almost 12 years until this lake is clean enough to use. And those are the basics of dealing with logs.